Space Telescope has a Cassegrain focus. Here's the Keck. Notice there's no side. There's no side on the Keck. There's nothing on the side here, but it has to have some kind of support mechanism for the secondary, and incoming light directly here, and then this honeycomb of segmented mirrors, 36 segment primary mirror. Then it has a focus here. It can come straight out in this Naismith focus, and then be used either here or in some room. And the Keck is a dual telescope that can be used for in the Hubble Space Telescope, I might have mentioned, it's close to my heart, so I was on a repair mission, helped have a mission critical piece for the repair mission, helped put its glasses on to fix it way back. Basically, it opens out here, light enters here, and then comes back through here, secondary, and then is focused back through here, through a Cassegrain focus. And then all your stuff, that you measure stuff with, back. Hubble's, the HST 2.4 meter mirror is designed for the visible, but also can pick up near infrared and near ultraviolet on the edge. Now here's the best possible ground-based image, and here's the Hubble image. And the thing is, if you blow this thing up, first of all, you can see a lot more detail. I don't know if you can see it so well from there, but if you see a good image on, say, on the web or something, you can see all the light here is just reflected back to you, so you can't see it so well. You can see there's a lot more detail, but you can blow that thing up and see incredible detail inside inside a small area here. It's really remarkable. Of course, the Hubble isn't limited by the atmosphere. And ground-based stuff is. Here's aspects of brightness and resolution. Brightness is proportional to the square of the radius of the mirror. So you double the size of the telescope, you get twice the brightness for a given exposure. As a given exposure time. So you just see a lot more stuff, a lot more stars, a lot more light. You can see farther. So also light gathering power. Light gathering power, since it's bigger, it improves the detail because the diffraction is less. And I think there's another picture coming up that shows that much better. Very good. Now here is the telescope size. That gives you the increasing size from A to B to C to D. It gives you the kind of resolution, 10 minute, 1 minute, 5 second, and 1 second, being arc second kind of resolution. So these are just bigger and bigger telescopes with the same amount of exposure. And they're very blurry. Here you can start to see detail, but there's extreme detail in here that is just not available. And if I look up there and I look here, gee whiz, there's no comparison. So, take a look at your text or e-text. You can really see this. A lot better pictures here. Okay. Let's see. Now here's the idea of resolving power. when two objects are close together, then they tend to sort of overlap, because if you magnify them with a good set of eyepieces, then you start to see the diffraction rings. So you got this, if you magnify stars, for example, then they'll start to look like this. If you don't have high magnification, you just look like points, but then you get high magnification, then you can see what's going on with the optics. And of course, if you have two stars right next to each other, and this thing is like this thing, then you can't really, they sort of blur into each other, sort of like this first image up here. So, but as you increase the resolution, that is, you increase the telescope size for a given wavelength, then you can start to see them as independent objects instead of blurred and singular. Okay. What you see in textbooks, what you see in a lot of these pictures, is not what you're going to see in a telescope if you view it with a book. You'll see, if you view Andromeda galaxy with a telescope, that instantaneous snapshot that you see basically with your eye, and it doesn't gather much light. So you'll see some foggy thing with kind of a bright spot in the middle. That's all you see. And you see all these other beautiful images. All of these other ones, I think, were actually Andromeda. Yeah, that's the Andromeda galaxy. So you don't see anything like this. You don't see anything like this. Basically, you see something more like this with some fogginess around it. That's about all you see. Now, you can make the telescope bigger, or you can gather more light by taking more light over time. Instead of just seeing what you see at the moment, you can gather it into a device that collects it. Photographic plates can collect light, so you can have some photographic film, it collects light and then expose it for a period of time, and so you can collect light and see much more detail over time. And it gets rid of a lot of fluctuations and averages and stuff like that, so it gives you a much better picture, much brighter picture over a period of time. But turns out there's these newer devices. Say astronomy back before the 60s or so, then it was governed largely by photographic emotions and eye-based kind of observation. But here, I guess it was in the mid-60s or late 60s, Bell Laboratories, there were Bell Laboratories out of Penzias and Wilson. This is also the CCDs were discovered there for purposes other than taking pictures. But charge-coupled devices basically use a photoelectric effect to accumulate charge based on light hitting. And then you can take that charge and then convert it into a number which represents brightness. And if you have a little filter over it, you can brightness of a certain color. So you can have pixels of either black and white, that's just brightness, or you can have pixels that are filtered, so you have red, green, and blue, so you get color. Now these things are much more sensitive than photographic plates. So therefore CCDs, their value is that they are incredibly sensitive compared to simple photographic film.
Higher order of magnitude.
Yeah, I wonder if we have a number, like I said, number sheet.
I remember in the textbook it said about 90% of light absorbed by photographic plates don't result in any data being shown, whereas CCD 5% is shown.
Let's see if we can, just had a graph up to show how sensitive before it came over here. In the visible range, a photograph has this kind of sensitivity. This is a log scale, 0.1, 1, 10, 100. And here's a CCD device. And so here's the visible between 400 and 700 in this range. And the photograph can do pretty well up to at least maybe getting close to the blue. But we have a factor of 10, maybe 70 compared to these two. So the sensitivity, at, say, in the middle of the spectrum is about, that's, it's probably 40, that's about 40 or 50 to 70 times photographically. So in the same amount of time, you get 50, 70 times the intensity or brightness. Therefore, you can see that much farther with the same exposure. And getting more exposure, then you get that much farther out. Now, you can, I don't know how many people have used Photoshop to change some kind of picture, to adjust something, to modify things. So you can modify stuff. Astrophotography, you take a photograph and you can bring out contrast, you can bring out colors, you can do all sorts of stuff to enhance the image. So just say taking an initial image, you can clean it up and bring out the detail. You can't bring out what's not there, but you can get rid of stuff that you don't want, and that enhances the detail. Image processor. So if you want to get into astrophotography, I would say number one, you put up with it, no problem. You have no problem with it. Now here's this atmospheric blurring due to air movements. We talked about that. And you can put telescopes on mountaintops. Then you have less sky to deal with. That's a good thing. If you put them in deserts, then it's drier, and you have less water vapor that also influences the degree to which the path is bent, and light is absorbed or scattered. So you can put telescopes in space. Fact is, if you have, say, a big mirror, not everything on that mirror is the same temperature. So there's parts here that are a little cooler, there's parts there a little warmer. There's parts of the observing container that are little, it's like it has its own little micro atmosphere. And you've got to control that in order to get the sharpest image. Because remember, we want to gather light and focus it. So if you have a small mirror, there's not much deviations that can go on because you're just dealing with small distance. But you're talking about a huge mirror, like the mirrors across this distance across the room, then huge, just a little tiny fraction of the temperature difference between these two can cause slight bending and slight distortion that would put things out of focus. So you can control that with computers and sensors and stuff like that. That's called active optics. Different than this adaptive optics. Active optics, controlling temperature in the local environment. Adaptive optics, you're adjusting mirrors in real time in response to the backscatter you get from a laser light beam going out. Area in a basin, and this Arecibo, and that's basically this whole ditch is stationary within this area. That was highlighted, I guess, highlighted in contact. 300 meters. And we can observe 24 hours a day. We get different information though too. So since it's different frequency, you're getting different information. Yes, correct.
The radio waves for radio telescopes have to be, have to like be set on an object as well? Or do they gather the waves much faster?
Well, it's still electromagnetic radiation. Now, you're gathering things fast because light comes in at the speed of light. Now, the wavelength means that your resolution is going to be different. Because remember, resolution has to do with wavelength and diameter. So now you have a big wavelength, so your resolution is much poorer. So you get this kind of blurriness. You can, there's not that much difference in collection time, probably. But you have to get enough energy. In other words, to get enough of an image, you need something bigger, and then you need to collect with a bigger dish to get enough energy to get a good signal. Does that help? Okay, we talked about interferometry, so it's especially helpful with radio. You can do that with, as we said, Keck can do interferometry. There are other places that have interferometers that are set up with visible with like telescopes. Now, I wonder if there's, okay, well, this is okay. Here we have a couple of things we can look at different wavelengths. Here is visible. All right. So you have visible of a nebula, and you see there's all this brightness, and then here is visible of looks like a smoggy area. But you take it at a different wavelength, you see a whole bunch of different stuff. Here you're seeing beyond stuff that's scattering visible light, but it doesn't scatter infrared. Infrared is longer waves, and therefore it doesn't get bounced around as much by dust and small particles in the air. So you can see through the dust. Here we got a lot of dust, a lot of bright glowing nebula and dust. Here we can see right through it and see a lot of detail inside. So the new telescope, James Webb, is an infrared telescope, and its main mission is to study the beginning of planetary formation. So planetary nebulas, or not planetary, but nebulas with a lot of dust and the forming stars. Then you can see through that dust you can see a lot of detail of the dynamics of these newly forming solar systems.
It also has a secondary mission in that it's able to see farther than visible light because it's at least.
Okay, well, this is just the same nebula taken with infrared. You can see the B here, infrared versus visible. And the Eagle Nebula actually has to do with, if you see this thing up close, that's the pillars of the creation and the picture, the famous picture. And see how much different it looks. That same area looks so different with the infrared. Okay. Now, for the high energy photons that are coming here, ultraviolet, X-ray, gamma ray, we can take very different kinds of pictures and see different types of astrophysical processes. And so these are very important wavelengths to look at. But you can't do it on Earth. That's got to be in space. So infrared, you can get to the near infrared with say, the Hubble, the near ultraviolet, but you need to get to the far ultraviolet, maybe especially maybe the X-ray and gamma, you need different types of telescopes altogether, and they have to be done, that has to be done out in space. Ultraviolet, most of it's absorbed by a certain type, a certain part of the atmosphere, a certain type of feature of the atmosphere. Anybody know?
Ozonal?
Ozone, that's right, ozone. So basically, oxygen will capture ultraviolet light and then form a different type of oxygen molecule, ozone, and that causes the heating, and that's basically where the stratosphere heats up. Like the stratosphere is the stratosphere. Okay, X-ray and gamma rays, you need to do these different types of ways to focus things. So you don't have normal lenses or normal mirrors. So you have this kind of glancing kind of guides that help focus these things. I wonder which this is. So in any case, X-rays and gamma rays often depict certain types of processes. Here we have a supernova remnant. Supernova remnant is the result of a huge explosion at the end of life of a star. I would presume this is a type 2 supernova. I'm not positive, but typically, if you have the star that's very old, if it's big enough, then it will run out of gas at the center and basically collapse on itself and then explode. And when that happens, basically a shock wave goes out and forms all the elements basically above iron on the periodic chart. Stars cook up all the elements except for hydrogen and helium, a little bit of lithium, and I shouldn't say cook it, they make them in one fell swoop, one very rapid process. So all the gold, all the silver, all that stuff, all the copper, that comes from supernovas.
Then just give it a couple billion years and those elements will combine in such a way as to start producing elements themselves.
I'm sorry, say again?
I said,
It's good to try to get my attention, otherwise I don't know what you're saying. Go ahead.
just give them a couple billion years and those elements will combine in such a way that they'll become intelligent and start making even more elements.
All right. Maybe. So, what's usually left is a glowing gas that has been blown off and something in the middle, usually something called a neutron star or a pulsar, we call it, will produce synchrotron radiation that is a continuous radiation, kind of rainbow, but different intensity than thermal radiation. And these kinds of things will also produce these different types of radiation spectrum. If we look at the Milky Way is our galaxy. And we can see the Milky Way at night not around here typically, but maybe you get to see it a little bit in the dark areas of Livermore up in Mines Road up there, but especially up in the foothills. You can start to get away from the city lights, and you see this band of white, the Milky Way. It's really stars that are in the plane of our galaxy. Now you can see. Let's see if we have a visible, this looks like the visible. Here's a visible picture, a visible light picture, and you see a lot of dark areas and bright areas. So it's the brightest here. Turns out that's in the constellation of Sagittarius. Tonight, Sagittarius will be there someplace. If you see a little teapot up there in the night sky, that's Sagittarius. And in Sagittarius is the center of the galaxy, towards Sagittarius. Now, if you look in the visible, there's a lot of dust that obscures what's going on in it. So to get beyond the dust, you would use a different wavelength. And here's infrared. Now you don't see the dust, you see more just the plain, light from the stars. And you can see something else, a bulge in the middle, and it's kind of thin, it turns out to be a disk. And you can go down to here's visible, infrared, and radio, see all sorts of stuff going on out of the plane of the galaxy. If you go to shorter wavelengths here, from visible to X, this looks like X as opposed to ultraviolet. And it's just a different picture. And here's a gamma ray, see a lot of gamma ray. And now the Milky Way is not considered an active galaxy. If you have an active galaxy, you might have a lot of stuff coming out here along the axis of the galaxy, and you'll see certain features, especially X-ray. But you also see radio loads. You see radio loads, but you might see a lot of X-ray intensity along certain places in an active galaxy. Active galaxy is something that where you have a supermassive black hole and a lot of energy, maybe stars feeding into it. So you have a lot of matter going into the black hole, and then it's coming in at a certain speed and spins up, and it spins up, then it